Okay. All right. Welcome, YouTube. Today we're going to be doing Grover's algorithm. Once again, this is actually workshop three. Yeah, and then the project will be implementing Grover's algorithm. So let's get started. Okay, it's there again. Okay, it's there again. I don't know. So first, we'll review the last workshop a little bit and the one before that, and then Grover's algorithm. So once again, I'll try and go a little faster through this, but the general state of a qubit we said is some linear combination of 0 and 1. We have these bracket representations, and we have these matrix representations. And when you measure a qubit, you have a probability to get 0 determined by the first coefficient squared, probability to get 1 determined by the second coefficient squared, and those two probabilities must add up to 1. And when you perform your measurement, you destroy the state. For multi-qubit systems, you have four possible states, 0, 0, 0, 1, 1, 0, 1, 1. You can stack them again into this matrix form, and you also have this bracket form. And that's the general state for a two-qubit system. Entanglement, we said, has to do with correlation between measurement outcomes of qubits. So in this example of a Bell state, if you measure 0 on the first qubit, then the second qubit collapses to 0 because uh, there's a ket 0, 0 in there, which means that a measurement of the first one that gets 0 will collapse the second one to 0. And then same thing, but with 1. Yeah. Questions so far? Okay. Gates again, the X gate will flip between the 0 and 1 state. And remember, the gates are linear, so you can distribute them to this superposition state, and then we can determine the action of X on a arbitrary state. Yeah, and then these circuit diagrams will serve us well with Deutsch-Chose as well. The Z gate will leave the 0 state unchanged, but multiply the 1 state by a -1 coefficient. So once again, like this, and then when you plot Z on a general state, you get alpha ket 0 minus beta ket 1. Hadamard will do the generate superposition. So on the 0 state, if you apply H on the 0 state, you'll get this equal superposition of 0 and 1. If you apply H on the 1 state, you'll also get an equal superposition, but with the minus sign in the middle. And yeah, question so far on the single qubit gates? Okay. Multi-qubit gates, the one we concern ourselves with is the controlled gate. So once again, you have a control register, which is this filled dot, and then a target register, which has a gate on it. And the action of the two-qubit gate is that it'll apply the U operation on the target qubit if the control qubit is in the one state and do nothing otherwise. Yeah, and we mostly use the C0 gate, which we draw like that. C naught, which is controlled X. Okay, questions on the recap of the gates and states? Okay. Deutsch-Chose, should I just skip this? It's not really relevant. Do you guys want to recap Deutsch-Chose? It's like I would skip it. Okay, yeah. But yeah, it was basically an application of just using those gates.
Maybe we can ask like, what do you guys remember from which shows last week?
Yeah.
I think it's specifically in terms of like what the black box did.
Yeah.
The Oracle, yeah.
You guys remember what two options we were kind of like choosing between for the function, whether it was this or that?
Constant.
Yeah.
Yeah. And do you remember how much more efficient the quantum algorithm is to the classical one?
Yeah, I just don't quite remember. Like there was like a minus state. Like there was this was.
Yeah, okay. Yeah, sure. Okay, here it is. So phase kickback is basically when you input, I'm going to skip the derivation, but if you input, based on how we define the oracle, which is this, that X and B pass into the oracle results in X, and then B XOR f of X. if you set the B register to the minus state, then you apply UF on some arbitrary X and then the minus state, what you'll get is -1 to the f of x, and then that same state back. So basically, some information about the function applied on f gets kicked back to the phase of the state after you apply the oracle. And that just allowed us to extract information about the function's value um, when you apply the oracle. So yeah, that we won't be using that in Grover's algorithm, but that was the main insight of Deutsch-Jozef. Yeah. And then here was the entire circuit again, where this part will generate the minus state, and then this H will apply will generate a superposition state, and then you apply the oracle in superposition, and then you undo the superposition to read out. Yeah. Okay. Yeah. And then we generalize that. Okay. Questions on the recap before Grover's.
So
Okay. So Grover's algorithm is a more useful problem because Deutsch shows up is pretty artificial. So let's define the problem. Formally it's called the unstructured search problem. So the input is once again a function f that maps from n-bit strings to single bits. So the same input of the Deutsch-Jozef algorithm. Yeah, so some function f, it takes n bits as input and outputs 1 bit. And same example, f of this 7-bit string if n equals 7, and it outputs some bit. The promise of the function is that there's exactly one input, so that's this x naught here, which is an input, such that when you input at that x naught into f, you'll get 1, but then for all other x, so all other possible inputs, then you'll get 0. So basically there's one secret input that outputs 1. Yeah. And then yeah. Again, the promise is a guarantee, so this is pretty much what I just said. There's some input that the function will return 1. For all other inputs, you get 0. And the output of Grover's algorithm is that secret string x naught. Yeah. Which we call marked input. Questions on the problem statement for Grover's?
is this like I don't know like for cryptography was like it's like a key that we need to find it, or is it?
It could be used, yeah, it could be used for cryptography, I guess. But I guess you might be thinking of like Shor's where you have to decode like RSA numbers, which are like
Yeah.
huge numbers. Yeah.
So mining is most similar to like Bitcoin mining. It's
Mm.
like it's like trying to find a needle in a haystack. You know how like when you know in
Yeah.
Bitcoin at the small service of just randomly guessing whatever string that'll give you this hash that like meets a certain requirement.
Mm.
Rovers is kind of like that in that like it's like the most efficient way to randomly guess guess.
Mm.
Yeah, and we call it unstructured search because there's no structure in the data. So if you might have heard of binary search before, which is an efficient search algorithm, but it requires that the database that you're sorting through is sorted. So in this case, that's some structure of your data. But in this case, there's no structure. And we're actually about to talk that the best classical algorithm to solve this unstructured search is just a linear search, which is where you just go through each element in order. Yeah. So here's just a quick example. If n equals 3, then these are your 8 possible inputs, 2 to the 3. And then these are your outputs. So what should Grover's algorithm return? Huh?
1, 0.
Yeah, 1, 1, 0. That input that has a 1 as the output. Yeah. Okay, this is what I was saying before. The classical solution. Yeah, and again, there's no structure in the data, so we can't use binary search. And I won't ask you guys because I just said it. The solution is to just brute force it. So you start with all zero string. Let's say you get 0. Then you go to the next one. Let's say you get 0 again. Then you go to the next one. You get 0. You get 0. You go again, and eventually you hit that x naught. And then you can terminate. And yeah, that's just called a linear search. So in the worst case, that you go through all 2 to the n bit strings, which are your possible inputs. So that would be if x naught is like all ones, right? One. Yeah, because you're going through each bit string in order. Yeah. And so that means this solution is exponential in size. So we use this notation of big O that it takes exponentially many queries, so calls to the function f. Yeah. And we will find that Grover's solution will give us what we call a quadratic speedup, where the order is square root of 2 to the n. And yeah, the caveat is that it's not always guaranteed to succeed, so we might actually output the wrong answer, but we will analyze the probability of this happening, that we don't solve the problem. Yeah. Okay, questions on the classical solution? Okay. Okay. So let's define some notation before we do the quantum solution. So let's define this ket A. That's a uniform superposition of what we call awesome vectors, which is the A in the middle. And so those are all the bit strings that satisfy f of x equals 1. And in our definition of the problem, we said that only one string, which we called x naught, satisfies this. So that means that this state, this awesome state, is just the x naught state. Yeah. So yeah. In that example where the string was 110, then we would have ket A equals ket 110. And then B will be a uniform superposition of all the bad vectors, which is the B. And so that's all the bit strings X that when you input them into the function, you get 0. And mathematically, this is how we define it. 1 over this root 2 to the n minus 1. That makes it a uniform superposition so that each vector has the same probability of being measured. And then we just sum up all the x's that are in the set B, which is just all those strings that are quote unquote bad. And I think I give an example here. Yeah. So if n equals 3 and if f of 101 is 1 and f of x equals 0 for the rest of the inputs, then this A is 101, ket 101. And then B is this uniform superposition of the other 7 inputs. And this 1 over 2 to the n minus 1 is a 1 over 7, so that each each string has an equal probability of being measured. Any questions on the notation? Oh, okay. Next thing we'll do before discussing the algorithm is how to express vectors in different bases. So let's say that this is what you're used to, which is a standard coordinate system, where the basis is a unit vector in the x direction and a unit vector in the y direction. So y will point up like that, and then x will point up like that. And let's say we have this vector, which is 2x plus 3y, and that will be at 0.23 because it's 2 steps in the x direction and 3 steps in the y direction. But we can choose a different basis if we so choose. So let's define our new bases as 1.5 times this x, and then plus y, and negative x minus y, in which case we can express the same vector as a different combination of the two, which is 2 times the first basis vector plus 1 times the second basis vector. And you can see that when you add up the vectors, which are these red and blue arrows, then you get to the same point in space. So those are different bases that we use to represent vectors. Questions on that? Okay. Um, okay, so in Grover's algorithm, it turns out that it will end up being convenient to express our vectors in the basis spanned by that awesome state and that bad state. And intuitively, that should probably make sense because we want to express how good our current vector is in terms of like how good it is, which would be the component in the awesome direction, and then how bad a vector is would be its component in the bad direction. So here's a quick example. Instead of vectors being in the standard basis, which is some coefficient C1 times all zero times 0, 0, 0, plus C2 times the next string all the way to C8 times 1, 1, 1. We have a different expression, which is capital C1 times A plus capital C2 times cap B. And then these are the definitions that we defined before with A and B. So it's just a different way of describing the same vector. Questions on that? I think I gave an example. Yeah. So let me go through the example first. So if n equals 3, and again, f of 101 is 1, then let's just make some random vector, which ends up being convenient, which is this. Psi is root 3 over 2 root 7, and then all these numbers added plus 1/2 101. That ends up being a normalized state. All the probabilities add up to 1. So this is a valid quantum state. But if we want to express this in terms of A and B, ket A and ket B, this ends up being 1/2 times ket A plus root 3 over 2 times ket B. And again, here are the definitions of ket A and ket B. So yeah, it's just representing any vector in a different basis. Any questions on that? Just keep it up for a little bit.
Someone else ask Adam online. And
Oh yeah.
you should be able to.
And I also have the chat up if there's questions online. Oh wait, what should I do? I'll just watch the thing, yeah. Okay. Oh, here's that same example where we just evaluate the numbers. So 1/2 is 0.5 and root 3 over 2 is approximately this number. Yeah, so that's our representation of the same state psi in this A and B basis. And here's the geometric picture of that, where this is the space, we call it the space spanned by A and B, which is a two-dimensional space because there's two basis vectors. And that vector psi is root 3 over 2 steps in the B direction, which is this red vector right here, plus 1/2 steps in the A direction, which is that vertical blue vector there. So then this green, when you add the two up, the green vector is the state psi. And the convention that a lot of people use is that B is on the x-axis and A is on the y-axis. So just keep note of that. Yeah. Okay. And also, I'll say we also kind of reduce the dimension because in this original expression, the basis was 0, 0, 0, 0, 0, 1, all the way to 1, 1, 1. Which is an 8-dimensional basis. And by changing it to the A and B basis, it's now a 2-dimensional basis. Okay.
Basis and dimension.
Okay. Yeah, and because it's 2-dimensional, we have the geometric picture. Yeah. Okay. Let me know, stop me if there's any questions, but yeah, again, it should hopefully make some sense why we want to do this because we want to analyze how awesome a vector is and how bad a vector is, which is how much in the awesome or bad direction is our vector, which will equate to if we make a measurement, will we get a vector that satisfies f of x? Will we get a string that satisfies f of that string is 1 or not? Yeah. Sorry, that it's a little abstract right now, but when we go through the algorithm, it'll hopefully start to make more sense. Yeah.
What's the probability of measuring that 1, 0, 6? Yeah.
Yeah, one. So the probability of measuring the 101 state, which is our good, awesome state, is 1/2 squared, which is 1/4. But if we had a vector, you can see, and that actually is if you project this vector onto the a-axis, it ends up being 1/4. But if we had a vector on this space that was like kind of up here, then it has a bigger component in the awesome direction, which means we have a higher probability of measuring a an awesome string, which is 101 in this case. Yeah. Huh. Oh, yeah. Oh, yeah. You didn't swear yet.
Is there any other like representation of the psi vector, or is it just in the spaces?
So you can choose an arbitrary basis to represent it, but in the case of Grover's algorithm, we want to choose this basis because we want to know how close our algorithm or how like how what probability with what probability we will measure a good vector if we were to make a measurement.
Like if we were to translate this to the standard basis, it would just be the previous.
Yeah. In the standard basis, it's this expression here. Yeah.
It's really just nice because we are kind of fortunate that the algorithm stays within the space the whole time, which is not something you'd expect from, going from a really large vector space to something that only has two basis elements. But since we can represent it with a small basis, then it becomes much simpler, right? Much easier to analyze.
Yeah.
So would it need to have like that 1/√7 in like all of the bad states to be able to reduce it?
So just our definition of the vector is that it should be normalized, the basis vector, which means that the probability should sum up to 1, which is why we have this 1/7 right here. Because otherwise, if you sum up the probabilities, you wouldn't get 1.
But if you were to have like a different normalized vector that didn't have √7 at the bottom,
So like giving different weights to these vectors in B.
you wouldn't be able to pull out the √7 as like part of B, right? Because it has to be n2 to the n-1.
Yeah, if you were to change the weights of the vectors in B, of the kets in B, then it would change the weights of the other one. So each vector would have an uneven weight. But in general, that becomes more complicated to analyze. So this is the simplest case. Yeah. Okay. Yeah, and this is kind of what I was saying before. So if we represent our vector psi in this A and B basis, and we wanted to perform a measurement then and there and say, did we solve Grover's algorithm? The probability of solving the problem or of solving the algorithm is just the coefficient in front of the A state squared because that's a uniform superposition of all the awesome vectors. So because we've expressed our vector in this basis, we can immediately analyze the probability of solving the algorithm, getting a correct solution. And obviously the probability of failing to get a correct solution would be mod c squared, prob to fail. Yeah. Okay. Oh yeah, that's exactly what I just said. Yeah. Okay, questions on that before we start doing the algorithm?
I have a quick question. Can you hear me?
Yeah, I can hear you.
Okay, sweet. So for the probabilities, if you like run the same algorithm several times, would it be like more likely that you'll be successful, or will it be just the same thing over and over again? So like if you don't get it the first time, you won't get it the second time.
So if you ran the algorithm multiple times and prepared the same state and then did multiple measurements, you would have a higher probability of solving the problem because you want to see how many of your results will like match, and then you can infer like how if you actually solve the problem. So if
Okay.
you know at the end of Grover's algorithm that you have a 95% probability to succeed, and you were to do that, and then you were to make a measurement, like maybe 10 times, then you could say with higher confidence that you succeeded by taking the majority of those ten measurements.
Okay, so it's kind of like a more efficient classical thing. We're just like doing it several times, but you don't have to do it as many times and just have a higher chance of getting.
Yeah, but in this case, to prepare the state before we measure, like we said before, it would be actually root two to the n, total calls to F, which we'll analyze soon. Yeah.
Okay, sweet. Thank you.
Yeah. Mhm. Okay, starting the algorithm, we're going to give a pretty simplified example on n equals 2, and then we'll just kind of carry on that example, which in the general case. So let's just say that f of 0, 1 is 1, and then the rest are 0. So obviously at the end, we want to output 0, 1 as our string. So now we can define A and B, now that we know this. A is this 0, 1 ket. B is this uniform superposition of the other three kets. Okay, now the actual algorithm, we start with two qubits that are in the zero state, that are both in the zero state. Then we create a uniform superposition by applying a Hadamard layer, which is exactly what we did in Deutsch-Jozsa as well. And then we can calculate the state after that, which is H tensor H on the 0, 0 state, which is this uniform superposition, tensor uniform superposition. We also call this the plus state and this the plus state. And you can do that, just you can distribute out the factors and get this. And this is a uniform superposition of all 2-qubit states. Because you have all 2-qubit states, 0, 0, 0, 1, 1, 0, and 1, 1, and they're all weighted equally with 1/2. So they all have a 1/4 probability of being measured. And in general, that's what a Hadamard layer does. Yeah, and now let's do that conversion to the A and B basis. And it turns out that we can express it as 1/2 times A, ket A, plus √3/2 ket B. And again, here are the definitions. So questions on that. So now we have the state of the vector in the A and B basis after we apply Hadamard layer. Okay. Now let's show that geometrically. So to give us a better idea of what's going on. So we just said √3/2 uh, of B in the B direction and 1/2 in the A direction. So it looks exactly like this, where we have √3/2 steps in the B direction, 1/2 steps in the A direction. And I've labeled this angle theta here, which is the angle relative to the B axis, and that's going to turn out to be useful to us. So let's quickly determine what that angle is, which is the inverse tangent of the opposite angle versus the adjacent side. Sorry, the opposite side over the adjacent side, which is 30 degrees. So yeah, this is the representation of our vector in this A and B basis. As you can see, also, if we were to do this projection onto the A-axis, this would be a component of 1/2, which means if we were to measure immediately after applying just a Hadamard layer, we wouldn't have a great probability of succeeding. It would only be 1/4. So we want to somehow boost this amplitude of the A state to be higher. Want to boost. So we want to get this vector closer to that A-axis. And then we'll perform a measurement, and then we'll hopefully solve the problem. Okay. Yeah, and this is what I was saying, that when theta is pi/2, then the vector is completely aligned with the A-axis. And then when we measure, we'll succeed with actually 100% probability. So that's our ideal case. Okay. Questions on that? The first step is just a Hadamard layer. That's the main idea. And we've expressed that vector in this A and B basis. Okay. Okay, so our algorithm will be iterative, so we'll do iterations, and per iteration, we're gonna apply some reflections on that A and B space, and that'll boost the amplitude of the A state, and it'll make the vector closer to that A axis, which means we can make a more reliable measurement. So, let's say we have this vector psi from before, and we want to do some reflections to get our state closer to this A axis. So, and we can only reflect along known axes, which are A, B, and psi in this case. So if we were to do this, here's the hint that 2 reflections are needed. So what 2 reflections should we apply to boost the amplitude of this state?
Can you reflect across B and then reflect across psi?
Yes, perfect. Michael, do you get that? I have a picture of that.
That's just
So here, let me show you the picture. So you start with psi, you reflect it on the B axis, and you get this blue vector, right? In the middle figure, right? And then you reflect the blue vector along the psi axis, and now you're closer to the A state. Does that make sense? So if you're theta from the B axis, and then you reflect it along the B axis, you're going to be theta on the other side of the B axis. And now this blue vector is 2 theta away from the psi axis. So when you reflect along the psi axis, you're going to be 2 theta on the other side of the psi axis.
Yeah.
And now your amplitude is closer to the A axis. Yeah. So perfect. So when we do those two reflections, we've changed the angle with respect to the B axis from theta to 3 theta, which is an increase of 2 theta. Yeah. So this is the key insight of Grover's algorithm, that we can just do this multiple times and get closer to the B axis or the A axis, sorry. And yeah, when you're closer to the A axis, you have a larger probability of solving the problem. So, yeah. Yeah, and again, this is the essence of Grover's algorithm. So you do some uniform superposition layer, which is Hadamard gates, and then just do these two reflections multiple times over and over again. So, and then you repeat until you're close to theta is pi over 2. Questions on that?
Basically the entirety of the algorithm. Breaks down.
How does it work when theta is greater than 4? Like, don't you start getting away from A?
So like by overshooting it.
Yeah.
Yeah, so you will end up, so at a certain point, you will end up overshooting the A-axis, which we'll analyze at the end, like how many times should we iterate to be as close to the A-axis as possible. Yeah. Okay. All right, let's continue. Okay, first step we just said was to reflect on the B-axis. So let's take some arbitrary state in that A and B subspace, which is C1 times ket B plus C2 times ket A. How do we reflect it along the B-axis? Here's a gate that will do that, and let's prove that it works. So this gate we call ZF, and Z is kind of like the oracle from before, and then subscript F means it has something to do with the function F. So ZF, when you apply it on X, will do exactly what phase kickback did, is it'll apply -1 to the F of X as a phase. So when it comes to actually implementing ZF, it'll be the same exact thing as phase kickback, but now that we know how phase kickback works, we can kind of take it for granted and just say, okay, ZF, this is what it should do. Okay, so internally, ZF will initialize a helper qubit in the state minus, and then it'll do what we said, and then it'll apply the oracle that we discussed in Deutsch-Jose. But in the end, this is the key result. Does that make sense? So we're kind of just taking phase kickback for granted now. Okay. Yeah. And because f of x is only one for all those awesome states, it turns out what ZF will do is it'll mark all the awesome states with a -1 coefficient. And for all the bad states, f of x will be 0, which means that ZF will do nothing to those states. Okay. Yeah. And here's that just in math. So if A is an awesome state, then you apply ZF on A, you get -A. If B is a bad state, if you apply ZF on B, you get B back. Okay. Good at that? Good on that? Okay. Yeah. And again, it's marking the awesome states with a -1 coefficient. And now it's actually pretty easy to see that this will apply reflection across B, because if we take our general state, which is psi C1B or plus C2A, then you apply that ZF on psi, it'll do nothing to all the B states, but then to all the A states, it'll apply minus sign. So then you get a global minus sign in the middle, and that's precisely a reflection across B, which you can see from the figure, where if you just take the coefficient in front of A and then multiply it by -1, you're going to get a reflection across B. Yeah, so it's still √3/2 steps in the B direction, but then the A direction gets inverted, which is a reflection. Does that make sense? Yeah. Okay. Yeah. Um, okay, yeah, here I just work it out. So in the previous example, when we apply the Hadamard layer, psi is this √3/2b plus 1/2 A. Here's the definitions of A and B again. When we apply ZF, we get on the 0 state -1 to the F00, on the 1 0 state -1 to the F01, -1 to the F10, -1 to the F11. So remember the gate is linear, so it just gets applied on each state. And now we can just sub in our F because we know F is only 1 for 1 0, was it? No, for 0 1. So then that 0 1 state gets marked with a minus sign. And then if we convert back to the A and B basis, we will get √3/2b minus 1/2 A, which is a reflection. So good on that. So you can call it ZF. ZF is the oracle in essence. So the oracle will reflect across the B axis. Good. Okay. Okay. That's what I just said. ZF is our oracle. And yeah. Okay. Yeah, this I pretty much said this. Oh, okay. So ZF again is our oracle because it encodes something about F. It adds that -1 to the F of X in front of the state. So let's just give an example encoding of the oracle. So let's say our same example, f of 0, 1 is 1, and then for the other inputs it's 0. Our oracle can be encoded using the following circuit, where the opened dot is a anti-control, which means it'll like be hit. It'll target the control condition. It'll activate the control condition if the input state is 0 instead of 1. So it's just the opposite. So in this case, if we start in a helper qubit in the 0 state, if the two input qubits are in 0 and 1, then it'll flip the ancilla qubit to a 1, and then it'll apply a Z gate, and we know a Z gate will apply a -1 to that. And then we apply the same gate again because we want to uncompute the result we want to uncompute the helper qubit back to the 0 state. But in essence, what this will do is that it'll keep these top two the same. And if the top two are in 0, 1 specifically, it'll add the minus sign. That's pretty much all it's doing. So I'll just leave it out for a second. But yeah, pretty much we're only swapping the ancilla from 0 to 1 if the two inputs are in 0, 1, which are denoted by an anti-control and a control. Okay. But that's an example of encoding the oracle. But when we're analyzing Grovers, we can just say we have an oracle, we know what it should do. We don't need to worry about how it's actually compiled to a circuit. Okay. Oh, I go through it. I go through how the encoding works. But I'll just go through the first example. So if you start in 0, 0, and then the tensor 0 means the ancilla is in 0. You apply the anti-controlled knot, then you get the same state back because the control condition here is 0 and 0, 1. And then you apply the Z gate on the ancilla, and Z on 0 does nothing, so you get the same state back again. Then you apply the same gate again, and you get the same state back. So literally the whole thing does nothing. But if you start in 0, 1, now the control condition is hit, which is 0, 1, which means it'll flip the ancilla to a 1. Sorry. It'll flip the ancilla to a 1. Then we know that Z on 1 will add a minus sign, which we can put in the front. And then the uncompute will flip the ancilla back to 0. But in essence, our output state has a minus sign in front of it now. So that's, again, just the encoding of the oracle. Does that make sense? Sorry if that was kind of confusing. And here are the rest, the other two. So it'll only do something for the secret string 01. That's it. Yeah.
You can assume the oracles of like which string is the correct one.
Yes, yeah, because the oracle encodes some information about our function. So instead, in the quantum solution, instead of passing in the function f itself, you pass in the oracle instead. So in the classical solution, if the input is the function f, for the quantum solution, the input will be the oracle, which encodes something about f. So yeah, this like big, this circuit right here is just like a big black box ZF, and then you pass that into the function, into Grover's algorithm. Okay. Okay. So that was kind of a tangent, but so far we have initialized the uniform superposition by just applying a Hadamard layer and done a reflection across the B-axis by just applying the oracle ZF. So here's just that in a circuit. You start with all zeros, you apply a Hadamard layer, and then you apply the oracle ZF. And then, yeah, the ZF will use some ancilla qubits, but we don't have to worry about those. Okay? So that's just the big picture. Okay, next step that we said, we have to apply a reflection along that psi axis, which will boost our angle by 2 theta. Okay, yeah, again, we need to reflect on the psi axis. And remember, we said that psi is a uniform superposition that we create by a Hadamard layer on the all zero state. So this is the literal definition of psi. This is what we got by applying Hadamards on all zeros. That's it. And so it turns out that the matrix form of the gate that will reflect along the psi axis has this form where you take 2 and then you have ket psi and then bra psi minus the identity. And that looks very confusing right now, but then let's quickly just show that it works. So I kind of just threw it at you and then we'll just show that it works. And then you've kind of proven that it works. Okay. Here's just quickly it on the example that we've been using where n equals 2 and the secret string is 0, 1. So if you apply H and a Hadamard layer on the all zero state, you get a uniform superposition of all two qubit strings. And then this gate that will reflect along psi, we compute in using matrix form where we have 2 and then that column vector times the row vector minus the 4x4 identity matrix, which is this result, which you don't really have to worry about. It's just an example of computing what that reflection matrix is. Because remember, all of our gates can be represented as matrices. So instead of giving you the action of the gate, I'm just giving you the matrix. Okay, now let's just prove that this is the right matrix to actually do a reflection with. So again, let's just say that we have a vector in the A and B basis that we want to reflect alongside. We're actually going to perform another change of basis, but it's going to be another 2-dimensional basis. So we can show them both with a nice geometric picture. So let's just say we have this purple vector right here, and we want to express it in the basis that is spanned by the psi vector and a vector that's perpendicular to psi. We can easily do that. It's just a change of basis. So the vector in the direction of psi is this red one, and the direction that's perpendicular to psi is this blue one, which we denote with psi and this perpendicular symbol. And we're not worried about the coefficients in front of them right now. Let's just let them be arbitrary because we know we can express the vector in this form. Does that make sense? The change of basis? Yeah. So with A and B, if you wanted to express in terms of A and B, it would be like this on A, then like this in B, but we've just changed the basis. Okay. Now let's just, should I even prove this? I don't even know.
So maybe skim through it.
Okay. So the fact that we're going to use to show that this matrix performs a reflection along psi is that psi and psi perp are orthogonal, which means that they have an angle between a 90-degree angle between them. So that means if we take what we call the inner product or the dot product you might have heard of, which is this ket psi times bra psi, if you do psi dot product with psi or psi perp dotted with psi perp, you'll get 1. And if you take the dot product of two different basis vectors, psi and psi perp, you'll get 0. So those are just mathematical facts of the basis that we're using. Let's just take that for granted and show this. Let's just apply a proposed reflection on the state in that basis and let's just see what it does. So here's our proposed reflection, and here's our state in the psi and psi perp basis. So we can just distribute it a bit. This first term will be this right here. And then this bra psi on this ket psi we know is 1 because of the orthonormality that we just said. The second term is this right here, but then we get a psi on psi perp, so 0, which is 0. So this whole term goes away. And then I on this term, you get this. Then I on this term, you get this. So let's just clean that up and you get this right here. Okay, these are like terms right here. We can just collect them together and we get this result where we get alpha ket psi minus beta ket psi perp. And just like what we said with the B reflection, this is a reflection along psi perp because we've just added a -1 coefficient in front of the psi perp state. So the component in the psi direction stays the exact same, but the component in the psi perp direction is flipped. And that's exactly what a reflection along psi is. And here's the geometric picture. So you can just stare at that and hopefully convince yourself that that does do a reflection. Or if it didn't make sense, you can just believe me that this gate will do it. Questions so far on that? Okay. Okay, I just gave you a matrix form. Let's actually use gates so that we can insert them into our circuit diagram. Let's just take the form 2 ket psi bra psi minus identity. Well, we know the definition of psi is that we apply Hadamard's on the all zero state, so we can just sub that in this red one and this blue one. When you do the bra psi, you have to change the order a little bit. But yeah.
Define what the bra is. So I think yes, it makes sense. It's the one that has like the angled bracket on the left and the living on the right. And basically it's just you're thinking about it as a vector. It's like transpose with just a pure vector, and there's the added detail that is also the complex conjugate, just because it's actually complex. So that's why, now the matrix will act on it from the right because it's like a real vector. But if that doesn't make sense, don't worry about it too much. We just have to flip the order and it's basically a vector.
Yeah. Okay. Now let's just distribute that 2 in there. And identity, we know that Hadamard n Hadamards on n Hadamards is like generating a superposition and then automatically undoing it. So that's the identity. So we can just sub in identity is equal to n Hadamards times identity times n Hadamards. That's just a substitution we're allowed to do because of this property. Now you'll notice that these two terms both have Hadamards like sandwiched in between specific gates. So we can factor those out. So the Hadamard sandwich, and then in the inside we have this term, we have this term, and then just an identity. And this gate right here, we're going to call Z naught. And it looks very similar in form to this 2 ket psi bra psi minus identity. And if 2 ket psi bra psi minus identity does a reflection along the psi axis, then Z naught where it has this form is a reflection along the all zero axis. And if that doesn't make sense, this is pretty much all it does. If you apply z naught on some x state, it'll add a negative sign if that x state was all zeros, otherwise it'll do nothing.
So it should be the opposite.
Wait.
Flip the cases.
Wait, why?
But if you acted on all zero, it stays the same. Otherwise, it's flipped.
I can't think right now. Okay, maybe it's flipped. Wait. Okay. Yeah, these cases might actually be flipped. So minus plus, is that what you're saying?
Yeah, just multiply the top expression by all zero states, still all zero.
Oh, okay. Okay. But anyways, yeah,
When you
it's
reflect around an axis, you flip all the other terms, you don't flip that.
okay. Yeah. Sorry. Like, yeah, this is what it's this should be positive, this should be negative. Yeah. Okay. Okay. Um, Z naught has nothing to do with the function f. So Z naught like is not like ZF in that it's passed into our function. Z naught will be the same for every function you input into Grover's algorithm. And here's a simple encoding of it, where the dots are anti-controls, where it's basically every of all the n qubits are anti-controls, and then you flip the ancilla if that control condition's hit, and then you apply z, and then you uncompute. So, I mean, I don't think you don't have to worry about it if it doesn't make sense still, but this z naught is like will be independent of the function pass. So this is just it expressed in gates. But in our circuit diagrams, we're just going to package this into one big gate, Z naught or Z0. Yeah. Questions on that? This is just the reflection alongside still, which, okay, yeah. So this was the reflection alongside. It was H tensor N Z0 H tensor N flex. Yeah. And that's this right here. So questions on that?
It's, yeah, because this is again, like the main equivalent, so if there are any questions, feel free to ask.
What does it mean by zero to the power tensor?
Oh, it means n Hadamard gates. So H tensor n is H tensor H, and then there's n H's. So you have n qubits and you apply Hadamard on all of them.
What if instead of H is zero, like the cat zero? Is it just
Oh, yeah, that's 0 tensor n is 0 tensor 0.
strings?
Yeah, it's n qubits that are all in the zero state. Yeah. Did we use that? Did I even use that before? I don't even. Okay, yeah, sorry. I forgot that we never really used that notation before. Okay. Okay, here's the big picture once again. So we have a vector in the A and B space, and we want to rotate it counterclockwise by 2 theta because that'll get us closer to the A axis, which is a larger probability of measuring and solving Grover's algorithm, right? And the way we do this is that we first reflect along the B axis by applying the oracle ZF, and then we reflect along the psi axis by applying H tensor n, Z naught, H tensor n. Does that make sense? And this is one iteration of the algorithm that will rotate by 2 theta. So we package all these gates into what we call the Grover iterate, which is this G, which is all those gates together. And so if you have some psi in this A and B space, you apply the Grover iterate G, it's going to rotate it counterclockwise by 2 theta. And that'll get you, in general, that'll get you closer to the A axis. Make sense? So what we did before was just derivation that this works, right? So, but in general, this is the essence.
For the Grover iterate, does it not matter that CF is above?
So you want to apply ZF first because so if you want to apply G on psi, it's going to be H tensor N like this, ZF on psi. And because of like how applying operators works, this one will be first, which is a reflection along B, and then you'll reflect along psi. Yeah. And also, I think in the notebook, this psi is called H because it's like a uniform superposition, but it's the same thing. Yeah. Okay. Yeah. And in general, it'll get us closer to measuring an awesome state at the end. Okay. And so if we start at an angle theta, when we apply a uniform Hadamard layer to the all-zero state, we get to some angle theta in this A and B space. And if we apply k Grover iterates, which is g to the k, so that's just g times g times g k times, the angle with respect to the B axis is now 2k plus 1 times theta. That's just rotating by 2 theta for each Grover iterate. Yeah. Does that make sense? And what did we just say? Oh, wait. Oh, so here's the circuit diagram to help you. So we start with all zeros. We apply a Hadamard layer, and then we apply the Grover iterate G, which is composed of the oracle ZF, which does the B reflection, which uses some ancillas. Then you apply Hadamard layer. This is supposed to say Z naught. And then H, and then another Hadamard layer. So again, reflect along B. Then this will reflect along psi. And all that is packaged into a Grover iterate. That'll rotate you by 2 theta. And then you just keep applying more G's. Yeah. Does that make sense? Yeah. Like just at a high level. And now the next question is, how many times should we apply G to maximize our probability of solving the problem? So we want to remember we said that we want to get as close to the angle pi over 2 as possible, right? Because if we're at an angle pi over 2, then we're completely aligned with the A axis, which means we'll have 100% probability of solving the problem. Yeah. Oh, and also in each Grover iterate, you're only calling the oracle once, which is right here. Remember, this is Z naught, which is counts as one function f call. So for each Grover iterate, you're calling f once. And remember, in the classical solution, we said we need to call f exponentially many times, which is in the worst case 2 to the n. Yeah. Yeah, that's what I just said. That last bullet. Okay, now how many times should we apply the Grover iterate? Which is what I just questioned. So remember, we want theta equals pi over 2 at the end, which would mean we're completely aligned with the a-axis. And we said that after k Grover iterates, the angle is 2k plus 1 times theta. So we can just set those equal to each other and solve for k, right? That'll give us how many times we should apply the Grover iterate. Let's do that math. I trust you guys can do the algebra. Distribute, subtract both sides. You get this value for k. Pi over 4 theta minus 1/2, which probably won't be an integer. So you usually take the floor of that number. Anyways, so let's compare that to the classical solution, which is exponentially many calls. If we want to do that, we're expressing it in terms of theta, which we don't want to do. We want to express it in terms of n, which is the input size. So let's just do some geometry. It's all going to be geometry. So this was just our example for n equals 2. But in general, this is what it'll look like for a general n, where when we apply a Hadamard layer at the beginning, the component in the b direction is root 2 to the n minus 1 over root 2 to the n, and the component in the a direction is 1 over root 2 to the n, right? So this would be the expression of that vector in the general case. And then this is n equals 2. You can check if you plug in n equals 2, you get that result. Okay. The tangent of the angle theta is the sine of that angle over the cosine of that angle. Sine of that angle the tangent will be the opposite side over the adjacent side, and just do some simplification, you get this, okay? That's the tangent of the angle. Okay, okay, now we make an approximation. N will usually be pretty large for these Grover problems, so not n equals 2. That was just a very simplified case. So we can kind of ignore that -1 factor and just say it's 1 over root 2 to the n, which is tangent theta. And also when n is large and theta is small, then tangent theta is approximately theta, which we call the small angle approximation. So if you remember the graph of tangent theta, it's a bunch of asymptotes like this. And if you look for small values, it'll kind of look like a linear curve. But I didn't draw it very well, but yeah. What can we say? Tangent theta is approximately theta, and 1 over root 2 to the n minus 1 is approximately that. So theta is approximately 1 over root 2 to the n. Does that make sense? So that's just expressing theta in terms of n using some approximations. Okay. Let's plug that into this. K equals this. We plug in theta, get this, and we simplify it to this right here. Oh, wait, do I do more? Oh, again, n is large, so root 2 to the n kind of dominates, so that -1/2 becomes kind of irrelevant, so we just drop it. So k is approximately this, and this is the exact result that I said at the beginning, that it's on the order of root 2 to the n calls, as opposed to 2 to the n, which is the classical solution. So yeah, k, remember, k is the number of Grover iterates that we apply. For each Grover iterate, we call the function once. So we get O of root 2 to the n. Okay, that's it for Grover's algorithm. Should we watch the video? No? Okay, if you're interested, 3 Blue 1 Brown is a YouTuber. He has a video on Grover's algorithm, and it covers pretty much the exact same thing that we just did. And these timestamps will be pretty useful to watch if you guys are interested. But yeah, that's pretty much it.
In like a real situation, how do you know, how do you represent it in like the basis A and B if you don't know what A and B are?
So A and B were just used to analyze the correctness of the algorithm. And that allowed us to get a result of how many times we should apply K. Literally, the only reason why we did A and B is just to know how many times we should apply the Grover iterate. When you're actually past a Grover problem, you're not going to have a notion of A and B anymore. You're just going to say, okay, this is how many times I should apply the Grover iterate. Then I'm going to measure and hope I get a good result. Yeah.
You don't have to change the basis atoms.
You don't know, not when you're actually doing an actual problem. Should we watch a little bit of the video? Maybe with here.
You guys watch this example way you went over there, or the thing I love with it, which is also second way of looking at it is easier that, and then look at the like code.
Into the code.
Code. Okay.
Guess you can watch this under the front and maybe
Yeah.
you can start next time with this. That's kind of like a recap.
Yeah. And just as a note, his convention, he uses K as the A-axis, B as the psi-axis, and the literal definition of B for the B-axis, which is a uniform superposition of bad vectors. Okay.
Get the picture again. The goal of this workshop series is we wanted to have you guys in the next few weeks like actually implement Grovers from scratch. So it's really not that complicated. We kind of explained it just now. As you can see, there aren't too many things to ask, just too many things. And then we're gonna run it on some real hardware. High school project, but next week I initially sent out the sort of tentative schedule, and we said we might skip like the midterms. And the week after that, we have that social. So if that still works for you guys, we'll do that. If you guys have any social like, restaurant requests, you can let us know.
And remember, what we just covered was proving that Grover's algorithm works. When it comes to actually implementing it, all you have to do is, where was it? Is this right here, where you just apply H and you apply Grover iterate K times, and we just told you what K was. So in essence, that's all you have to do. Yeah. Okay.